What a great crowd we have today. Awesome. Thank you all so much for being here. This is wonderful. I know I blasted emails out to a lot of people, and I'm just so happy to see a lot of faces of people who have supported Capstone in various ways. So welcome to the Senior Capstone Symposium for the class of 2026. Alright, so here's what's going to happen today. You won't hear too much from me because I want to get straight into the students' presentation, so this is the order. We're going to have 5 teams present and then take a quick break. There's going to be some food, sandwiches, and snacks set up outside for you all. And then we'll come back and do the remaining 4 teams and try to get you wrap up right around 1 o'clock. The students have been working so hard all year, especially this past semester, getting their projects together. So this is really exciting, and I hope you all, I know it was really hard to get to this point, but I hope today feels really celebratory and you can feel really proud of yourselves and all your peers, because it has been such a pleasure for me to work with you guys. So much joy, so much fun. I'm just so proud. You all have been so dedicated to your projects. I'm sorry to any of your other professors that you have not been giving as much effort in their classes, but you've done an awesome job in Capstone. So really want this to be about y'all. Celebrate this, have fun, celebrate each other. Before we get into the presentations, I'm going to say just a few things about the engineering department at Wake Forest to give you a little bit more context. And so this is our 6th graduating class. Our engineering department is unique in that we offer one interdisciplinary engineering degree, and it's grounded in the Wake Forest liberal arts tradition. While we have a very unique and flexible curriculum, it's also AVET accredited, so we align with all the national standards for engineering programs. We also deeply embody the Wake Forest motto, Pro Humanitate, in all of our classes from year 1 up to senior year, and especially in Capstone with these project-based courses. So Pro Humanitate means for humanity. So with everything we design, everything we do, we're thinking about who we're designing for. We also have this idea of the whole engineer. So beyond the technical skills that you get into the engineering classroom, we think about the whole person, not just developing technical skills, you're developing as a person. So our engineers are amazing when it comes to a lot of the professional skills that industry is looking for. And then our department values are integrity, empowerment, inclusion, growth, compassion, and joy. And so I think that'll come out today as you see the students present and talk about their projects. Capstone Design, this is a year-long experience, and it's meant to be the bridge between their foundational education and going off into the workforce or grad school or whatever that might be. The idea is to build from all of their previous courses and work on real-world problems that have real applications. They have expert technical panels. Many of the guests here today served on those panels. And they also work with a lot of difficult standards and constraints, and often that are in conflict with one another. And they're also supposed to think about the social, economic, environmental impacts. So there's a lot more than just the project. We have them dig deeper, think critically about a lot of other aspects of engineering design than just getting the project done. And these are our 4 pillars. And if Sydney's here, she made us a new logo. Thought Dr. Crow would be happy about that, of the 4 design phases. All right, so we're gonna jump right into it. So I'm gonna ask Cooler Heart to come on up. And I've got handheld microphones so everyone can hear, and I have a clicker. And right before I pull up your presentation, I also wanted to show this really quickly. This is everyone who's been supporting the seniors. So I didn't properly introduce myself. I guess I'm Courtney Vittori. I'm the lead instructor and do a lot of coordinating, but it is like a huge team effort pulling off Capstone. So a lot of faculty help, a lot of staff help. These are all of our technical experts. We've also had sponsors. So I'm going to bring this up at the end, but I really want to acknowledge everyone who helped get them here. And let me pull up Cooler Heart.
Testing. Good morning, we are the Cooler Heart, a heart transplant shipping device, and this is our team. I am Darcy Kate.
I'm Paul.
I'm Anna Claire.
I'm Jared.
And I'm Jacob.
So let's get started. So what is the leading cause of death in the U.S.?
Heart disease.
Wow! That is the right answer, heart disease. More than 600,000 people died in 2023 from heart disease. This number could have been lowered if they had a better access to heart transplant. And currently, there are more than 3,000 on the transplant list. This number also currently could be lowered if there's a better access to heart transplants.
So while medicine has advanced in incredible ways, heart transport is still fighting a battle against time. The current problem right now is the 4-hour limit. What does that include? If you think about it, it's the time to procure the organ, the time to the hospital, to the airport, the flight itself, and the time from the airport to the hospital. So this doesn't just put pressure on the surgeon itself, but literally like geographically limits the reach of the organ, which you can see here. We have like 2 donor hearts, which in that current like 4-hour limit can only reach in this kind of circle. With even just 1 more hour, you could literally reach thousands of more donor recipients that you can see here.
Right, these are the 2 main solutions that are currently on the market. On the left, you have the classic ice cooler, which is literally just a cooler with ice. The heart is placed in the cooler, and this is a problem because it unevenly cools the heart, meaning that some areas of the heart get too cold while others get way too hot, and that impacts the viability of the heart. So to combat this, the Sherpa pack on the right was created. Now it's temperature regulated. It keeps the heart between a certain temperature, a cool temperature, and as you can see, the heart is submerged in a preservation solution. However, the Sherpa pack is still limited to a 4-hour viability window. The Sherpa pack is still limited to a 4-hour viability window. So based on these solutions, we identified 4 key innovations that our device needs to have. Firstly, our heart needs to be preserved between 4 and 8 degrees Celsius. We need to actively pump a preservation solution through the coronary arteries that provides nutrients and oxygen while removing waste. Third, our device should display temperature, flow rate, and oxygen concentration data so that we can monitor the viability of the heart throughout transport. And finally, we'd like to have an efficient workflow, making it quick and easy for clinicians to use while maintaining sterility, meaning that the heart can be directly taken from our device and transplanted into the patient.
So this is our device. If you really think about it, in order to really implement the 4 key innovations that we decided, we used a term called hypothermic oxygenated perfusion. So the 2 main devices that are used today are basically just glorified, drop the heart down to a specific temperature, and then hope that it really survives. Ours actively improves upon this by transporting nutrients throughout the heart, as well as improving the temperature capabilities of it. So this is our device really blown up. So the heart is placed in a perfusion solution. This solution contains all the nutrients that the heart needs in order to survive the transport. This solution is then pumped, moved to the pump, which is then moved to our cooler. Based around this, our flow rate is taken and can actively be regulated throughout. From the cooler, our solution is then moved to the sensor bath, which allows us to actively see what the metrics of our solution is. This solution is then moved through our oxygenator, which is very key in making sure that the heart has the oxygen that it desires. And then this loop continues throughout in order to make sure that the heart is regulated to the best capabilities it can be.
One key feature of our device is the active perfusion. We wanted to make sure that our device mimics the way that the heart actively pumps blood through itself giving it oxygen and nutrients while carrying away waste. To do this, we created this custom aortic cannula that's inserted into the aorta, not allowing flow up through the ascending aorta and down through the aortic valves. So that fluid is diffused through the coronary arteries, allowing for that full circuit to complete and reducing the shear stress on the tissue walls here. On the next slide, you can see how this cannula is integrated into our canister through an easy snap-on mechanism. On the right, you can see the different parts of our canister, and on the left, you can see how it's secured into the device. This double layer is made to protect sterility while allowing easy workflow with the clinical workflow. And here's how it works. After the heart is cannulated, it can be snapped on to the lid, and this is placed into the canister. From there, the outer lid can be connected and then placed into the carrying case. Tubes are connected to the top, and the oxygen can be turned on. The flow and coolant can be turned on, and then the device can be easily wheeled away for transport.
Now, while in transport, we're monitoring 3 main viability metrics using our 3 sensors: our temperature sensor, our flow rate sensor, and our oxygen sensor. And all of these sensors have a feedback mechanism. So for example, if our temperature sensor detects that our heart is reaching the upper limit of our temperature range, which is 8 degrees Celsius, it'll tell the cooler to cool down the solution even more to make sure that our heart stays within the 4 to 8 degrees Celsius range.
On arrival to the recipient, the canister lid can be removed, and the inner lid and the heart there can be introduced into the sterile field. From there, the heart can be disconnected from the inner lid, and this allows for easy integration into the current clinical workflow.
So what we've done this semester. At this point, we've basically completed the very basic beta prototype that includes everything we could possibly need for our device. We have the entire circuit set up already, as well as a battery system, and this basically makes it untethered to to any wall basically. So it can be transported in an ambulance, in a helicopter, on an airplane, as well as the active monitoring system that allows us to adjust any parameters that the heart basically needs.
So then looking into future development, a few potential viability metrics that could be also assessed to see if the heart's viable is lactate and calcium. And then if we had had more time, we would have made the Cooler Heart app. Now, this app would track the location of the device during transport so that the receivers could see where it is, as well as they could also see the metrics of the heart currently so that they know what's going on as well. So, thank you.
For questions, if anybody has a question for the team.
What are you measuring? What are you actually measuring temperature of, and where is that temperature sensor?
The temperature sensor is in the sensor bath, and it uses. Let's go back to here. So you can see this sensor bath here, and this is our. I'm sorry, this one is our temperature sensor. So it just measures the temperature of the current solution that is flowing through the circuit. It's not directly in the heart canister because it was not possible for us to maintain sterility and have like a good workflow by doing that. But we put a different sensor bath externally close to it so we can still manage the temperature.
So you mentioned you're cannulating through the aorta. Where does the perfusate come out of the heart? Go back into the circulation?
So after the fluid flows through the left and right coronary arteries, that would dump out into the right atrium. From there, that has an open vent into the canister where it just flows out into that bath where it is.
Yeah, and we have the tube coming out of the bath, coming out of the heart canister back into the circuit.
One more.
Yeah, well, so what was the biggest challenge you overcame so far? The hardest thing you did, and then what's the biggest one left?
I mean, at least for me, I think we distributed our tasks very well. So I think we all have our each own specific, like, different challenges. Like for me, my hardest challenge was definitely trying to figure out the electronics aspect of it and connecting the battery to make sure that that we have enough battery storage and to make sure that the actual, like, current doesn't, like, it's very smooth. But again, it depends on what everyone did.
Okay. All right. So next up, in case y'all didn't see, is Bridgerton.
Good morning, everybody.
Good morning.
We are Team Bridgerton. My name is Matt,
I'm Khalees.
I'm Joseph.
I'm Charlotte.
I'm Esteban.
and we are Team Bridgerton. So, what is our capstone? Our capstone is actually quite different from everybody else's, because instead of being given a problem and coming up with like a solution that is pretty freeform, it could be like really anything, we're actually given a stringent string of rules because we are competing in the Student Steel Bridge competition hosted by the American Institute of Steel Construction this year. And so what that is to design and build a 1 to 10 scale steel bridge, as you see over there, parts of it over there, over the Rio Grande River in El Paso, Texas. So we're actually given a problem statement, but we're given such stringent rules that we have to follow. And so that's kind of like where everything from our project comes from. And so also part of this is because this is a recurring competition every year, part of that is to build a workflow so that future teams can improve upon our process, because this is our first year doing it.
So the problem here is a bit hypothetical, more than anything. Thank you. So yeah, you can go to the next slide. Thanks. All right, so the requirements here, it's focused on the idea of serving the El Paso community, connecting communities there. It has to span over a river and be able to carry pedestrian loads, so nothing too heavy, but also being safe enough to support that. Within the competition itself, it has to be constructed within 30 minutes. And also, if it's deemed safe enough by the judges and the rules, of course, it has to support a 2,500-pound load. So for the scoring, it is divided into 3 categories. It's the structural, construction, and the aesthetics. Structural is more about the dimensions, the deflection, the sway. The construction is based on how fast you build it, the number of builders that you have on your team, any fines or penalties that occur based on the rules. Aesthetics is more on theming. Do you paint the bridge? Do you have your name on the bridge? Any designs that you have or that you add to it, stuff like that to make it like nice and pretty. There's also a poster that you have that's required for the competition as well, and that's all about showing your design, justifying why you chose that design in particular. So our opponents here, NC-A&T was the host, so we went to Greensboro this year. Clemson, USC, UNC Charlotte, and Horry Georgetown Technical College in South Carolina, those were all the schools involved. So for our timeline, throughout the entire fall, we did a lot of background research, benchmarking, finding what other teams did in the past, what their designs kind of look like, and then narrowing down to settle on what kind of truss we wanted to use for our longitudinal truss, things like that. Early spring, in the January-February time, we ordered our steel, started spending a lot of time in the studio, cutting steel, welding, grinding, all those things. And March and April, that's when we started practicing our assemblies, seeing how fast we could build everything. And of course, April 4th is when we went to the competition. And so the rest of this April has been all about what worked well, what didn't work well, and what we can, provide for the future jobs that we have.
So, once we establish the problem, it's now time to formulate a solution with what we're given. And so first, we need to kind of figure out where does our bridge actually need to go, And so our bridge had the span between these two areas for footings. You can see two on the left and a big one on the right. And then our bridge has to fall over the top of the river without actually touching the riverbank. And so that's kind of like the dimensions we were given by the competition. So within those competition rules, we had to develop our system requirements. So we had a bunch of system requirements because there's 62 pages of rules. And so it was a lot of fun to develop that and kind of go through that process. But eventually we got into where the calculations became important and figured out how can we build a bridge that fits within the rules but also holds the load and does the requirements we need. And so first was global strength. That's kind of like how much it can take in terms of the vertical load. We had global deflection, which is kind of like how much the bridge bends down when load is placed upon it. We had our footing buckling, where the footings are the ends of the bridges. How much force can they take directly vertical into them? Because all of the weight of the bridge and the weight of the load is going into it. Then we had our 3 bolts, our 3 bolt different categories. And so our shear strength, bearing, and tear all dealt with like how much force can the bolts themselves take at our connections, and how much can the plates that hold the bolts hold them so it doesn't tear out. And so you can see we had a lot of different calculations. This is only a small snippet. But we also got to have a lot of experience with Reset 3D and simulations. And so a lot of these calculations showed that our bridge needed different modifications. So we went through 3 different prototypes before finalizing on like a more final design, which was then reworked in fabrication. And so again, a bunch of calculations. We worked on sustainability in the top left. We made sheared moment diagrams, and then we found our safety factors for everything, which are all above 110%. So finally, we came up with our 3 components: the longitudinal truss module, the transverse bracing, and the footing. These 3 pieces are basically copied and modularized and then put across the entire bridge, and that's formed our full 24 feet. So you can kind of see it there.
Next, we're going to run through the steps of the construction process. So the first step was to purchase the materials. We wanted to order a little bit more than what we needed, but obviously not too much to keep the budget in mind. Next, we wanted to cut the metal into the desired lengths. This ranged from around 3 feet to as short as 6 inches. And then we were to grind the internal rod members. We calculated using Sokotoa, obviously, that it was around 17 degrees.
So then once we had our materials prepared, we moved into the fabrication of the longitudinal trusses. And due to the small space that we had in the welding booth, we had to develop some specific workflows to help improve efficiency and speed. And you can see here sort of how we did it, where we clamped the top and bottom cords to the table and then welded the internal web members from there. And then we welded plates onto the top and bottoms of the footings, both to improve surface contact area with the ground and also provide a surface for connections to the longitudinal trusses themselves. Then we laser cut out some plates using the metal laser cutter for the edge of the longitudinal trusses to bolt them together, as well as matching this shape with the transverse to make it one seamless connection point. So then when we were welding those onto the bridge, we went through and set them up each at a time to ensure that every connection point would be in line, so that when the competition came, our bolts would go straight through the holes and we wouldn't have to do any muscling around or run into issues on the day of the competition.
Okay, so at this point, you now have a bridge. Well, not really. You still need to assemble it. So this is a pretty big bridge, 24 feet. Can't really do it indoors. So we went to our football stadium, and we're out there in the sun for 2 days practicing. And you know, we learned a lot. I feel like during our first run through, our construction time was about 34 minutes, which not good within our scope or what we wanted to do. But while out there, we did simulate the different constraints and the playing field that we would have. So yeah, practice makes perfect. That's us during our first one. You can see this is Wake's first time doing it, so again, a lot of it was just trial and error, seeing what worked for us. And yeah, key takeaways. Our nuts and bolts should be kept separate. I know, shocker. And our bridge should be assembled over the river instead of in the construction zone, which seems a little redundant, but worked for us. And yeah, again, what I said earlier, practice makes perfect. By the end of our practicing rounds, we got it down to about 26 minutes. And yeah, competition results, that's us in front of our built bridge. So this is real time, not sped up at all. That was our bridge, that's us building it. By the end of the competition, I'm just gonna skip past it, 23 minutes, which is a school record, if I say so myself. So yeah, through practice, we really knocked the time down, got it in a fantastic range, really developed a workflow that worked for us, and yeah, got into a good flow. And
So yeah, after our competition, of course, we want this to be done for future teams. So our key takeaways for next year is in both design and competition. So first of all, the importance of tolerancy. We got hit pretty hard because of some of the tolerance of our parts, and so we wanted to make sure that that was a key takeaway to remember for next year. And then also lateral bracing and prioritizing joints are other things we're going to write about for other teams for next year as well. And then for the competition itself, everybody liked how our design was relatively simple compared to everybody else's. Everybody else tend to over-engineer a little bit. And so we want to tend towards that next year as well and go over every rule and build a consistent workflow that others can use for perpetuity. So that is coming soon. Thank you.
We don't have time for questions. We're going to go straight to the next team. Awesome job. You can probably catch them during the break period if you want to ask them more about the competition. Next up is Boomay's Booey Boys. Yours is PowerPoint, so I'm going to open it up. Oh, wait, it's a Google Slide now. Okay. And I had to download it so you can see it. Okay, you want to use the slides version? Oh, yes. But I tested this to make sure. For some reason,
Welcome everybody. Really appreciate you guys taking the time to come to this symposium showcase. We're Booey's Booey Boys. My colleague.
Hi guys, I'm Niels.
My colleague.
Jillian.
My colleague.
Blair Bishop.
And we're covering portable wave power, which is essentially taking wave energy and translating that into electrical energy. So, to begin, who here has been to the beach and surfed before?
Oh yeah.
Cool. Well, personally, I've never been. But my colleague Niels has in the Philippines. Niels, tell me about it.
Hey guys, so yeah, I like to go traveling with my brothers and we go surfing quite a bit. You can see us there, handsome and all. And when we're out there, we spend a lot of time waiting for that perfect wave and you're sitting there buoyancy up and down. And you kind of think there and sit, all of this potential energy is going to waste. We need to fix that. So that brings us to a problem. So, our target here is in the Philippines. In the Philippines, there's over 4 million households that don't have access to reliable electricity. They're so off-grid that there's no way to give them cable and stuff like that. So they're living off these diesel generators, which only gives them about 2 to 3 hours of power a day, which makes it kind of difficult for them to refrigerate things, such as food and medicine. This kind of inhibits the growth in these communities and doesn't let them expand.
So we've been talking a lot about waves. There are a lot of waves in the ocean. Okay. Right now, everyone in coastal rural islands, in the Philippines specifically, use diesel generators. Very costly, very polluting. So we had an idea. And this idea is going to create consistent, reliable energy. We're going to capture the energy of the waves. So here is our prototype, the float goat. Originally, we wanted to have a buoy encasing all of this, but due to time constraints, we never made it that far. So what we have today is the mechanical and electrical systems that take a wave's power the buoyancy bringing it up, anchored to the ocean floor ideally, that's an assumption we're making. It'll take the energy going up and down and turn it into power for a battery. And this battery can be used to help charge things like phones and lights.
So looking at our different systems, we have our mechanical system, which you can see on the right side of the screen. So the input is the recoil starter, which has a rope attached going through the bottom. And this creates mechanical energy by rotating the shaft. And this good then propagates down through the bevel gearbox and the planetary gearbox. And then these gearboxes cause the flywheel to spin, which then causes the generator to spin and generate electrical energy. Then the energy is amplified through our electrical system, the boost converter and charge controller, and eventually we are charging the battery. And this can be used for electricity. So here's what it would look like in an ideal situation if our system was floating. You can see that the rope is actually anchored to the ocean floor, and as the waves come, the system rises and falls. So we assumed that every single wave in the Philippines would be half a meter tall and take 4 seconds to occur, which is obviously not true, but in order to model, that's what we used. And each time a wave, half meter, came, the recoil would rotate at 20.8 rotations per minute. And then this is amplified by the 1:15 gearbox, planetary gearbox, which will result in almost 4,000 RPM. This eventually leads to 42 watts being generated per every cycle, every wave. So Blair is going to demonstrate our system working. And for some more context, half a meter is about knee height on some people, and 4 seconds is about the length of a long breath. So you can see Blair is pulling, and he's taking 4 seconds to pull all the way down. The first rotation...
This is flashing, by the way, that means it's charging.
Yeah, it's charging.
I can pull it again in a sec.
So we start with 20.8 RPM, which is about the speed of a slow bicycle pedal, if you can picture that in your mind. And then the flywheel is rotating at almost 4,000 RPM, which is about the speed of a kitchen blender. So it's very quick. And then for each time Blair pulls, 42 watts of power is making it into the battery. And this is enough to power lights, a laptop, multiple phones. So it's sufficient.
Thank you, Julie. So now we're going to look at some of these impacts on the communities that we're going to be doing. They're going to be giving access, energy access about 10 kilowatt hours per day. That'll be enough to charge cell phones, refrigerators, and it provides a clean, renewable offshore power to all of them. For sustainability, they're going to be cutting out all emissions, so there's going to be no cost in that, as well as pretty much a zero operating cost. So it's going to save up to about $5,000 a year, which is great. The coastal communities will then have those 4 million households powered, and we're going to bring sustainable growth to those remote areas. And so, okay. So, our buoy is estimated to cost about $2,000. These diesel generators typically cost $1,000, but with the calculations, I think we're going to be able to pay back that premium with just under 2 months of using this device.
Wow. In a collective effort, we bring light to every shore. Thank you, guys. Our group really appreciates all the help we got in throughout the year. It doesn't matter if it's another team member, it doesn't matter if it's any professor. Everyone's so willing to help. We really appreciate it.
Does the rope have a tensioner on it to ensure that you apply constant tension depending on the size of the wave?
No. So that's one of the assumptions that we're saying is that it always has tension, but we know that once it is anchored and there is a buoy involved, we have to look more into detail about how is that slack going to be addressed. So we have not figured that out.
The anchoring system is something we didn't get to at all this semester, so we had to make a lot of assumptions on that end. Dr. Hensley?
What were some of your material considerations for just the sustainability of the actual system being in a kind of volatile environment and saltwater waves, etc.?
So we used stainless steel for the internal components, the shafts and the gearboxes, and then the outer frame is just aluminum, but we made sure to not use any metals that would be harmful if it was placed in an ocean.
And we do assume that the buoy that would be surrounding it would be very protective, or at least mostly protective of everything in here and letting anything out. So that sort of membrane helping it be sustainable.
And temperature?
So we say temperature.
Like say your electronics and things, are they going to be able to handle high temps?
High temps, I mean,
In which,
like, you mean like just overall heat on the system in the
Yeah,
sun?
I mean, it's floating out there.
Float out in the sun,
In
yeah.
the Philippines.
I don't know.
They chase into a
yeah, ideally we would have a buoy, which was also not developed this semester, and ideally we would use a material that protects the internal metal components that are possibly going to be heated by sunlight. We would
Probably like for
protect
some
that.
really like heat resistant electrical components, some sort of insulation.
Stuff is balloon works.
Testing. Good afternoon, we are Balloon Works. I'm Katie.
I'm Amelia. I'm Lila.
I'm Julia. We're excited to talk to you about our project today. Disease. It's inevitable. We all get it. You can't avoid it. As we age, just one particularly annoying disease occurs in your arteries where there's a buildup of plaque. Right along there. What happens is your artery narrows with this plaque. Blood can't flow through as well. As a result, you get a risk of blood clots that can lead to strokes, heart attacks, also causes pain, overall distress because you're in pain and worried about the risks. Well, luckily, there are treatments, and it's your choice. You can choose very invasive surgery, that's right, a large incision and some fun recovery time, or you can have a small tube inserted into your artery with just a needle poke. I would prefer this method. This method is an arterial catheter that is inserted into your artery, a blood vessel, and fed through the blood vessel until the instance of disease. Well, how does this work? At the tip of this catheter, this thin, flexible tubing, is a balloon. A balloon is coated with drug. The balloon is inserted into the instance of plaque, into your artery until you reach the instance of plaque, and then you inflate the balloon. This simultaneously opens the narrowed artery and administers drug to prevent the plaque from returning because the balloon has drug again over the top of it. Once you expand it, it is administered to the arterial walls. Now this is great, but what if I have a lot of plaque? I have many instances of plaque all over my body. Well then, I'm going to need one catheter for one instance of plaque, because you can only have one balloon coated in drug before you have to withdraw it and insert another one to treat another instance of plaque. And then there's another one. That's a lot of balloons and catheters, and I would like something very quick and easy. Well, Advanced Catheter Therapies, a company we've been working with, has developed a catheter called the Persona Occlusion Perfusion Catheter. With this catheter, instead of a drug-coated balloon, you have balloons without drug and there are two of them. They inflate, and the space between them is occluded. It's isolated from the rest of your blood vessel. In this space, you can now deliver toxic drug. And it's not going to get to the rest of your bloodstream because you do not want this drug, it's very toxic, in the rest of your blood. And now you have treated one instance of plaque. Well, I have others, let's say a few inches down the artery segment. Well, I can just deflate the balloons and move on, reinflate and administer more drug. Saves time and number of catheters, so money. How does this work? Well,
so we love Persona OPC, but there's one major issue. And I would show you guys, but that would take too much time. So I'm just gonna explain it. So the Persona OPC is a highly manual system. You have 3 separate endoflators that you're using to administer the drug, and you're checking pressure as you're doing this. So I don't know about you guys, but I don't really want my physicians stressed out while they're inside my body. It's a super complex workflow, super high risk of error, like just so much stress is going on. Here's Katie, a little visual. You can see the 3 separate endoflators, lots of time. Again, this is the method all out in steps. No thanks. I really don't want that. So as a group, we thought, how can we fix this? This brings us to our solution, which is one automated closed loop control system. Here's a CAD drawing that you can see. So with our system, you can automate infusion, and it also gives you can have pressure control, and it gives you real-time feedback. So normally when you're doing it manually, you have to watch your endoflator and make sure that the pressure doesn't go too high because you're gonna burst an artery, and nobody wants that. But with our system, it does this automatically using 2 motor-driven syringe pumps that you can see here. And yeah, real-time feedback. It's great, and it's fewer steps, which gives a lot less stress for the clinicians.
So a little bit more about our physical prototype you can see here and how it is integrated with the existing OPC. This is one of the main things we wanted to do, is make sure that it was easy to integrate with the catheter. So you can see we have 2 motor-driven syringe pumps. One motor is responsible for pushing fluid in and administering the drug. That's connected to the inflow port. You can see the blue arrows. And then a second syringe pump is responsible for pulling fluid out, and that is connected to the outflow port. You can see the red arrows there, and you can see the fake artery right here. So we'll show you a little bit of a demo, if we can. So if you can see, the blue fluid is flowing in and the red fluid is flowing out, and you can see that artery right there. It was once red and now it is filled with blue drug and to treat the patient. So you can see that this is regulating the pressure and automating the system. So instead of the physician using those endoflators, looking back at the pressure sensor, our system handles that all automatically, and that's where you really see the shift from a manual process to a controlled and automated one.
So what are the benefits of our system? The main thing is we've reduced the time the procedure takes to infuse the drug from 2 minutes to 45 seconds. We also have many fail-safes within the system. Our biggest one are these limit switches. As the plate moves towards the front and pushes drug in or pulls the blood out, we have these limit switches on the front and back ends of each one, and it's hit, that means the system automatically stops. And this is just in case there's a communication issue somewhere in our code or something just goes wrong, we can safely say, oh, this will stop itself. And then also we have programmed into our software that the pressure will not go past 760 millimeters of mercury or 1 atmosphere. This pressure is how much the artery can withstand before it starts to get damaged. Additionally, if it goes past that, you're going to blow by the balloons and basically cause the drug to escape everywhere, defeating the purpose of this particular device. So we also have many different ways to work with the system. We have our remote control, which works with our screen, and the screen will show you the lapse time of the procedure, so you're aware of how long you've closed off the artery, because we don't want to keep that closed too long, because then you're going to have dead tissue, kill the artery, really bad stuff. And then you have your dwell time. So this is how long you let the drug sit inside of the artery, and this basically allows it to infuse into the artery walls. And program into this, you can have, it's a minimum of 30 seconds with a maximum of 2 minutes. If time outside of that is placed, well, the system basically says, you can't do that. And then we have two places where you can have to twist these thumb screws, and what happens is that when you twist them, you can lift up the plates and then you can replace the syringe. So if you need to add a new syringe full of drug because you need to go into more sections, you can do that. Also, at the end of the procedure, often physician will use a saline flush. They'll push saline to basically clear out all the drugs so that when they do take the balloons off, deflate them, they can then prevent any actual of the drug then going into the rest of the system. Basically, pain, well, no more. Multiple blockages, no, a singular procedure. We are improving patient care one procedure at a time. Thank you.
Time for one question. Lots of pressure.
Sanitation.
Is the company you're working with going to take this and put into trials and things like that, or is this more of like an average senior student? Like, do you think they're going to run with this?
That is an excellent question.
We hope so, but
yes.
we don't know.
That's we've been working with some of the lead engineers and the CEO of the company, and so they're very much so involved with the process and been really great about giving us feedback about what they got, what feedback they received from physicians, and basically what they might want to see and what would work well with the current workflow. And so theoretically, yes, that would be really, really nice if they would do that.
They are dormant right now, but
Yeah.
fingers crossed, maybe.
Fingers crossed. The company they first released the product right before COVID started, so it really could not kind of get off the ground because no one was doing what's many ways.
It's too difficult, but
It's in many ways can be elective surgery because it's a different and new, and so yeah.
Thank you.
Thanks.
Awesome. One more team before the break is Team Helios.
Good morning, everybody. My name is Scarlett Johnson.
I'm Keenan Trey.
I'm AC Fatini.
I'm Ryan Swilling. I'm Natalia Beckford.
I'm Devin Topman.
And today we're going to be talking about our unique solution as a mobile solar power unit for the city of Winston-Salem. So I'm going to start with a little bit of a background. This project was proposed to us by the city of Winston-Salem. They acknowledged a gap in between a current solution for charging medical devices during power outages. People who live at home who need life-sustaining measures aren't going to be able to charge their devices during power outages. And so with this, we also noticed there is a 2.5 million nationwide and 3,000 people in Winston-Salem who need a solution for this. And so our job is to create something that's human-centered. We want it to be easily deployable for the people who are going to be deploying this. We're working with the fire department and emergency personnel, but we also want this to be easily interactive with those who need to charge their medical devices. We want it to be quick and efficient and want them to be able to do this easily. And so that brings us to our main considerations with this. We wanted to look at several different factors that might influence our design, socially, economically, and environmentally. How do we want this to be viewed? This is something that is going to be used by the city, and so how do we want people to look at this as something that the city is deploying for them? And so we factored this down into three main components. We want it to be accessible for people. We want it to be renewable energy, clean. We don't want to make a huge impact on the environment, and we also want this to be affordable, something that can be mass produced maybe. And so with this, as engineers, we also want to quantify what this will actually do. And so we came up with main system requirements. So we want this product to store 14.4 kilowatts of hours. This is equivalent to charging a 600 watt medical device. It's pretty heavy duty for 24 hours at a time. Hopefully after 24 hours, we have electricity back on. And we also want this to be durable. If this is going to be deployed during electrical power outages, we know that this is going to be during natural disasters likely. And so we want to be able to withstand a 100-year storm, which is equivalent to 102 mile-per-hour winds, means no tipping. And then we also want this to be deployed within 30 minutes. This is quick response for people.
So for our overall design, we modified an easily deployable 5x8 trailer that is already compatible with pre-existing emergency personnel vehicles. And then we also designed for solar panels, which provide clean and renewable energy, but also require very low maintenance once deployed. And then we will have a battery cell unit that will store this energy, and as well as electrical conversion devices, which get this solar energy into the batteries and then the batteries out to these medical devices. We also accounted for safety features, such as stabilizer jacks for tipping, remote shutoffs in case our system's not performing to the level that we needed to, and as well as a fire extinguisher in case of any electrical fires within our trailer.
So the main goal of our system is to convert sunlight into usable electricity. So through the electrical system, we do this in 4 main steps. Obviously, when most people think of solar, they think of solar panels. So we have 365 watt solar panels wired in series that take sunlight and convert it into raw DC electricity. However, this electricity is not compatible with our batteries, so that's where the charge controller comes in. Think of it as like a smart translator. It takes the high variable voltage from the solar panels and converts it into a clean, steady one that our batteries can use. The one we use is a Victron MPPT, which is a maximum power point tracking charge controller. So that basically just squeezes as much power from the solar panels depending on what the sun is doing. And from there it goes into our custom battery pack. We have a 48 volt lithium iron phosphate battery pack that has, like Scarlett said, 14.4 kilowatt hours of storage. So that's enough to power an entire house for about half a day. So obviously the batteries are needed because there's not sunlight all the time. And then from the batteries, the charge goes into the inverter, which converts it from DC electricity into AC, which is the same as any regular wall outlet. So people can then just plug in their medical devices and it will work.
Okay, so I did a wind load analysis for our structure, and I wanted to figure out the amount of internal weight that needed to be added to our structure to prevent it from being tipped over. So I used a programming language called MATLAB to do this. And as we said before, our system requirement was for our structure to withstand 102 mile per hour winds. And so in order to do this, I created a MATLAB code that calculates the tipping force. And I used apply for our right wheel reaction versus our wind speed. And so the blue line represents the reaction at the right wheel, and the dashed line represents our tipping moment. And the tipping moment is basically when the applied wind force causes the structure to rotate around its center of mass and causes it to fall over. And so what I did is that I kept our MRI value of 102 miles per hour consistent, but in MATLAB I tested to see the minimum amount of weight that needed to be added in order for our structure to be successful. And so you can see the red dot, I added 450 pounds to the internal weight of our structure, and it's above the threshold, which means it's in a good area and it's not in the danger zone.
And then looking at analyzing our structural design of how we're going to have the solar panels on the trailer, there are basically 2 parts to the design. And so on the left, we have the brackets that will hold the 2 panels on the roof. And then so that we can maximize our power, we wanted to have a panel folded down on the side as well. And so that's where the rack on the right comes in. And so to analyze this, we used a software that allowed us to simulate the loads and look at our specific materials, the specific weights of the panels and the wind, and adjust the materials as needed. And then we've moved on to fabricating our structure. And so that started with assembling the triangle brackets, adding additional supports to make sure that those brackets could withstand the wind. We welded a steel rack for the side panel, and then we're working on finalizing our rack system, which includes adding gas struts that will assist in lifting the panel because we just want to maximize the ease of deployment.
Moving into our electrical fabrication, so we had to test each battery cell manually and individually. We had to make sure that each battery fit our system requirements to make sure that our system can output the amount that we advertise. And then we had to modify each battery terminal. So we have 45 battery terminals, and there's 2 on each side, so in total it's like 90. And we had to drill and lift up each terminal and put a screw in between. And we had to do this safely because lithium ion phosphate batteries are highly dangerous, so we had to make sure that we did that safely. And then also we connected each battery group with compatible wiring just to make sure to connect them in series and parallel. And then we incorporated circuit breakers as a safety mechanism to make sure that to prevent it from overcurrent and to prevent short circuits.
So a little bit where we are now, we're about 85% complete with our fabrication process. We got most of the solar panels on top, working on the last one, and then electrically wise, we just need to wire everything together. We're making really great progress. We've actually been able to present this project to the city, and that's us with the mayor in this picture. And this was just to kind of show where we are, and everybody was really excited about this project. So I want to say thank you to everyone who's helped donate and contribute their technical knowledge to our project. Thank you.
So we all have a quick break. I'm going to ask to take the Q&A into the break if you want to talk to this team. So we're going to take 10 minutes. I know that's not that much, but there's some food if you need to use the bathroom, and then we'll come back for the rest of the meeting. As possible. I know it's so many questions we'd like to ask and like to know more about all these projects. We're going to let the Reawakening Strength team go ahead and get started.
Hey everybody, thank you guys for coming to our presentation. We are Reawakening Strength. Our project is the bed bike. We focused on one problem: patients lose leg strength in the hospital quickly. So our goal was to design a system that helps them stay active while still in bed. For the agenda, my team will walk through the bike mechanics as well as the electrical components, talk a little bit about the underlying conditions of deconditioning, and talk a little bit about revision and our impact.
I'm Peyton.
I'm Luke.
I'm Abby. I'm Hannah.
I'm Musa.
Just introduce us. Okay, to kick us off. So what is deconditioning? Deconditioning is the reversible decline in physical function that results from prolonged inactivity. And so in our case, we're looking specifically at hospital-related deconditioning, so patients that spend their time in the ICU and are not able to get up and move around. And so why do we care about this? Because in just 1 week, you can lose 10% of your muscle mass, which can have a trickle effect that leads to further health complications, such as muscle atrophy, pulmonary and cardiovascular decline, reduced bone formation, and eventually a complete loss of independence.
So it's clear that the effects of bed rest are both rapid and measurable. Patients can lose approximately 1.5% of leg strength in just 1 day. Resting heart rate increases by about 0.5 beats per minute per day, and up to 95% of hospital stay is spent inactive, whether that's in bed or in a chair. It's clear that the clinical need is really urgent, and this recovery needs to begin at day 1. So a lot of these pre-existing in-bed exercise devices are either unstable, limited in functionality, overly rigid, or just too bulky for practical clinical use. These limitations reduce the usability and also reduce the effectiveness and use in a wide range of patients.
Now, what's our mission and what do we want to accomplish? Our goal is to transform patient recovery by fostering holistic healing through movement. This bike will minimize deconditioning and muscular atrophy to improve patients' recovery.
So we are a continuation project, so we were very lucky to have a very successful prototype to work off of from last year. So we used this and to build our prototype, and we learned from some of their points that could be improved, and this is where we mapped our design inputs from. So these lie within the stability, the adjustability, the organization, and having the option to pedal on the floor. So as we move through all of our design choices, they'll all be mapped back to these points that we identified at the beginning. So our proposed solution is shown here in this model. And so going around just to talk about some of the features, it is compatible with the Stryker hospital beds that are widely used in Wake Baptist in the ICU. This is that adjustability feature that we wanted to have, and so we have it so that it can be moved to fit each individual patient. For prioritizing organization, we encapsulated all of the mechanics inside of this housing. And then on the other side of the housing, there's a screen that we're going to get into later that displays all of the metrics and patient progress as they pedal. With the mechanics, our electronics are also cased inside, which helps with that organization, but also maintains accessibility for access to the components during the prototyping phase. And then we'll show it in a video later, but this piece can actually be removed and placed onto the floor so that the user can pedal either sitting in the chair or over the edge of the bed. And then lastly, the setup is done in less than 30 seconds with no tools. It's lightweight so that anyone can pick it up, and it has these handles for easy grab.
So now onto the mechanics of the bike. Based off those 4 prioritizations that we shared earlier, here are the ways that we're going to incorporate those into our design. So firstly, for stability, we're going to keep the same motor and the flywheel. We decided to do this because the motor was a good motor and it provided smooth power, and now with a new set of bevel gears, that smooth power will be felt by the patient with the pedals. The motor is also a compact design, so it'll fit nicely into the housing itself. For adjustability, this was one of our top priorities, and we wanted something that was quick, useful, and simple. And so the thing that we decided on was a car seat slider, just like underneath the seat of everyone's car here. It's something that's out of the way, it's not intrusive, and it's really familiar with everyone that would be using it, and it would provide 8 inches of movement, so it would be able to fit any patient that's in the bed. For organization, we wanted all of the critical components, so the electronics, the mechanics, the screen, all to be in one enclosure so that it's easy to carry and it's portable. For floor use, we wanted, as the patient moves through like the recovery cycle and they get more mobility, from being able to use the bike in the bed to then on the floor sitting in a chair was one of our top priorities as well. So just being able to pick up the bike off of the bed mount and put it on the floor with no tools required was a necessity for us.
Now looking at the electronics. So as Peyton mentioned, we had a pre-existing bike. So with that being said, the electronics were fully functional. So a lot of our focus was ensuring that the wiring was more organized and making sure that this new electronic setup could fit into our new integration of our bed bike housing. So as you can see, this is the previous team's electrical setup. The power supply is internal. And the wiring is not that clean, as you can see. There were actually some components that were not fully connected. So with that being said, the extent of our work was to deconstruct this to get a better understanding of what was going on with the electronics. We then had to conduct some calculations to ensure that when we were reassembling everything, that nothing was burnt out or went bad. And then we began to reconstruct for our beta prototype, which is this one shown on the screen, to see how it would fit onto our slab, which we decided to add an electronic slab, which would go inside of our bike housing to make sure that it would fit on this size constraint. So through tedious planning and a lot of digital formatting, we came up with our alpha prototype, which is this one imaged here. This one we had solder connections, and we made sure to bolt the components onto this board. And this board is a wooden board that is now our electronics slab. So all of this was to focus or achieve our focus of organizing the wiring and to allow for easy integration into our bike housing. And this allowed for us to be able to remove the electronics for easy access for any sort of debugging that's necessary or any sort of future iterations needed.
All right, so here is a high-level overview of the bike's electrical system. So the first thing that happens is the user pedals with optional motor assistance. Then the system tracks, so that's where the sensors come in, tracking the user's movement in real time. Then the data is processed by the brain of our system, which is the Raspberry Pi 5, supported by the Arduino Uno. Then feedback is displayed in the form of metrics that are displayed live on the screen that the user can see. And then finally, the workout is saved and logged in order to track patient progress. This is what the user interface actually looks like to the patient. So first, the patient can click on our application, Reawakening Strength, and that launches the homepage of our application where you can add a user. Once adding a user, you can begin the workout, but you can also set programmable distance and time goals in order to make your rehabilitation customizable. Once you set these goals, your metrics will track in real time, including power, cadence, time, distance, and even encouraging messages that pop up as you're pedaling. And finally, as soon as you finish, a workout summary will appear that summarizes the averages of all of your metrics. So we've seen the electronics, we've seen the mechanics, but we haven't really seen how all of this comes together as a product. In this video, you can see that it's demonstrated how you can pick this up off the ground, assemble it quickly and easily, and it's really made for a seamless use for both the patient and the clinician. Here, Hannah is demonstrating what it would look like for a patient to actually be using this in bed, and this product encapsulates all of the priorities that we talked about before. And then our impacts can be seen across multiple different people and locations. First, faster patient recovery, which is really important to us, which also leads to shorter hospital stays, which means that hospitals can use their resources more efficiently. Care can be simplified because physical therapists can assign customized workouts to their patients. Treatment can be personalized. Outcomes improve because rehabilitation can start from day one, and this progress can be quantifiable in the metrics that are tracked by the system. We are Team Reawakening Strength, and we are proving that rehabilitation does not need to wait until you're out of bed. We'd like to acknowledge all of these people for their insight and for helping us bring our ideas into a tangible product. And now we'd like to open it up to Q&A.
Don't have time for questions, but there's a showcase due on Wednesday. So awesome job, y'all. You did a great job. All right, type ship. Yeah, there's three.
Oh, you guys are gonna go. All right.
Yeah, I got you. Nice job, mate. We'll see once we get it.
Hi everyone, we're Type Ship. I'm Olivia.
I'm Catherine.
I'm Zach. I'm Reese.
Gavin.
I'm Chase.
And we're really excited to share our project with you today.
Okay, so our project, for those of you who don't know, was to build an electric boat and take it up to Portsmouth, Virginia and compete in a 5-mile race against a bunch of other schools. It was hosted by the American Society of Naval Engineers. It was the Promoting Electric Propulsion Race, and it was regulated by the U.S. Coast Guard. We competed in the manned planing division, which basically means that there's somebody on the boat driving it, and ideally the boat comes up out of the water and gets on plane.
All right, so here are broader impacts and our purpose. So first, we're advancing innovation. So electric power in marine crafts is a newer kind of thing. So we're trying to push this forward. And then we're reducing environmental impacts. So electric power, as opposed to the traditional ones, are cleaner and quieter. And this is a continuation project. So we're working off of last year's type ship design and pushing this forward. So.
Holding this sleep boat together is a Fastcraft XR14 hull that is made for gliding across the shallow bodies of water across the United States. In the front, we have a battery storage that contains 2 units, holding up a total of 32 batteries. In the center, we have our center console that holds our steering system and our startup. And in the back, we have our gear system, which connects to our 50 horsepower outboard. And all the way at the end, we have a Stingray Classic 2 Senior hydrofoil, specifically made for reducing drag.
Yeah, so talking about the batteries, last year's design had a huge battery box in the front, which made it very top heavy. So this year we were taking it and trying to organize the weight a little bit better. So this time we decided to do 2 smaller battery boxes that fit just the right of 16 batteries in series on each side, and then we connect them to parallel. And then they will go farther in the back. Also, we made it was strapped in with a latch, so we made it more accessible with a lid and a hinge.
Okay, so for our motor and controller, we're using the same ones from last year. Basically how they work is we take our DC power from our batteries, it goes into the controller, and the controller switches it into AC power, and basically tells our 20 kilowatt 3-phase brushless AC motor how fast to spin. There was a lot of troubleshooting to do with this that was unexpected because it did work last year. Catherine and I think, called Arden over at Thunderstruck Motors, who made the motor, I think 1,000 times, and he was getting super fed up with us by the end of it. But eventually we got it working, we thought, and then we eventually got it on the water and figured out that the system works a lot differently when it's put under load than it does when it's not under load. Nevertheless, we got it working, finished the race, and yeah.
Yeah, so we took a 50 horsepower Yamaha outboard, gas powered, and we took out the gas engine, and then we put the electric motor on top, and based on the power that was getting outputted from the electric motor, we decided we want to do a gearbox. And the idea was we want to make the propeller spin faster, because then we go faster. That's the whole idea of the race. So we went through the process of scanning the outboard, and then designed the gearbox in CAD, and then we ordered the parts and did a lot of machining, implemented it, and it worked great. So the way that the outboard works is that there's this rod that you can move up and down in order to change the direction of the propeller spins. So we wanted to kind of give the driver a control system in order to change which direction the outboard was going. So we designed this electrical system with a linear actuator and a microcontroller, and we got it fully implemented, and then we took it on the water, and we spun, I wish you could hear this video, it's awesome. We spun the motor the wrong way, and it destroyed the linear actuator. And unfortunately, this was like a week before the race, so we didn't have enough time to replace the components, but the system does work for next year's team.
Yeah, so getting a little bit into our manufacturing processes, there are 3 main components that we manufactured, custom built to fit the components that we already had. So those include the gear system, the battery boxes, and the center console. And so in order to manufacture them, we used processes including but not limited to welding, grinding, the CNC machine, laser cutting, etc. And then we also did maintenance on some of the existing components that we had, like the hole here, which you can see in the leftmost picture. It had some cracks, and so we had to seal those with marine bondo, and then we ultimately did a gel coat and a wrapping to make it more sleek in the water. And then this middle picture here shows Catherine replacing one of the parts in the outboard.
All right, and on-water testing. So we went to Salem Lake to test our boat out. Here's some really cool photos of Catherine and I testing it. We got up to 25 miles per hour. And this is kind of where we figured out when the motor was under load, how we were having issues. So the boat was kind of stopping and starting. So this is really important. Looking back, we should have gotten in the water earlier because then we could have figured out issues earlier. But yeah.
All right, results. So like Libby said, we got up to a top speed of 25 miles per hour. Unfortunately, due to some of the complications with the batteries and the load that we were putting on the propeller, this did not happen in the race. And so we had a 38-minute time. With that ultimately got us 4th place out of 11 teams. And so in some ways this was disappointing, but talking with the other teams at the competition, we kind of realized that almost every single team was having similar issues. And so ultimately finishing the race at all was a pretty big accomplishment. We were one of 6 teams, so only about half the teams finished. And so at the end of the day, we're proud of our work and we accomplished something pretty good.
So we want to talk about some lessons learned because I think it's important for us and for future teams. So the process of this type of project with a hard date and a competition, it's pretty tough because you're learning a lot, but ultimately you have to make decisions. And sometimes we made decisions that I think we would like to go back and change. For example, like a few weeks before the race, we were kind of reviewing our power calculations, and essentially we realized we didn't have enough power to go to our motor, and that was likely a source of a lot of our issues, but we did not have the budget nor the time to add more batteries to our boat.
And then on the battery side, we made a pretty bad assumption at the beginning that we didn't need a battery management system. That was based on the fact that last year's team did not use one, so we were like, all right, I guess we don't need one. That was wrong. You can see the picture of Gavin on the top right holding our 2 batteries that lit on fire during the race. Those are now in a waste barrel at the trash. So battery management system for next year is definitely needed. Another thing is that, like we found out once we got out on the water, stuff is going to go wrong that we would never think of that they might go wrong. But again, it will happen. That other picture is us at, I think, 11 p.m. the night before the race in the hotel parking lot with a power cord hanging out of the hotel window, getting stuff done, making sure we were ready. Overall, though, it was a huge learning opportunity for all of us, and there's so many valuable lessons that we look back on and we're just really proud of.
Yeah, here are our acknowledgements. We want to thank everyone who helped us out. Big shout out to Greg, Dr. Crow, and Nick. And yeah, thank you so much for listening.
So y'all, we're gonna keep going to the next group to get you out of here. Awesome job. If any of you can stick around, I'm sure there's lots of folks to talk to you out.
Type shit.
Alright, what's going on, guys? We're Oregon Trail, and we're going to be presenting on our project, the Pan Express, extending time and expanding access, and we're really excited to talk to you guys today. So here's our team, and let's get straight into it. So what's the problem? The problem is that there are 28.7 million Americans diagnosed with diabetes, and for people with late-stage pancreas failure or other complications, really a pancreas transplant is the only curative treatment. But even when there's a pancreas available and someone who needs it, there's a bunch of difficulties getting that pancreas to where it needs to go.
So currently the standard gold method for organ transplants is static cold storage. That's basically how it sounds. An organ is placed in a bag on ice inside of a cooler. And with this, with this method, the pancreas specifically, it's only viable for about 12 to 18 hours. I know that sounds like a lot of time, but with coordinating everything and actually getting the organ to where it needs to go, this window of viability can close pretty quickly. As well, there's no oxygen delivery, no circulation, and no real-time viability assessment. So unfortunately, a lot of organs are discarded. And going a bit more into that, about 10 states in the US have no pancreas transplant centers. In 2020, 346 pancreases were discarded when being recovered for transplant. And in 2023, the non-use rate hit 23%. That's about 1 in 4 organs discarded, simply because of time and geographical barriers. But that's where we come in. Our device, the Pan Express, is a portable normothermic perfusion system that recreates life support outside the body.
So y'all are probably wondering what normothermic perfusion is. So it's simply just tricking the organ into thinking it's still in the body. We're able to do this by keeping the organ at normal body temperature, which is roughly 37 degrees Celsius. And we're also able to pump perfusate through, which is pretty much like fake blood. And that way we get oxygen and nutrients to the organ. And unlike static cold storage, this allows the organs to be put in more of a physiological state, not only increasing the health of the organ, but ultimately making it more viable for transplantation.
So what does our system actually look like? So our system consists of 2 separate fluid loops. The first one starts in a perfusate reservoir where it is pumped into a central oxygenator. There it combines with the second fluid line, which consists of a heated water bath that continuously pumps heated water to heat the perfusate up to 37 degrees Celsius. The perfusate also undergoes oxygenation through the O2 tank before it makes its way to the pancreas. On its way to the pancreas, it undergoes sensors for temperature, pressure, and oxygenation, our system requirements, to ensure the pancreas is receiving optimal normothermic perfusion. After it perfuses through the pancreas, it returns back to the reservoir, completing the circuit.
So that's a lot, but we were able to break this into our subsystems when assembling and developing. And the first one we started with was our main perfusion system. And so we paired a lab-grade parasolic pump, which is used in industrial applications, to an inline pressure sensor, and we controlled both of those via an Arduino. And the reason we did that is so we can get real-time data, which you can see in the graph in the corner. And parasolic pumps are naturally pulsatile, which is good in mimicking the body's heart rate, but bad when you're trying to get accurate readings. So we used a mathematical filter to get a linear line, which you can see more so in the gray. And that helps us get good data and actually control the speed of the pump, which in turn helps us control the pressure in the system as a whole. And to get accurate readings of pressure, we use a manometer, which you can see in the pillar in the corner right there. And that allows us to check the pressure of the fluid throughout our system and compare it with our pressure sensor. And we 3D printed a model pancreas with internal resistances that match real pancreases, so we could get real-time data as testing continued. And then on the next slide, we had to figure out where we were going to put it, and we reached out to Yeti, and they graciously donated a cooler to our team. And you might be asking, why are we going to put a warm system in a cooler? But it's a perfect way to isolate our system from outside environments, and also Yeti's pretty cool. Like, they sent us this massive cooler, why wouldn't we use it? And so the walls inside the cooler are super slick, and we didn't want to tamper with the actual integrity of the cooler. So we used a beverage divider, which fits into the slits inside the cooler, and that gives us our rigid base to build our fixture onto. And for the fixture, we used aluminum 2020 extrude, which allows for rapid prototyping and ease of manipulation as we continue through our process. And then as we got to further stages and everything was done with each subsection, we were able to fill it all inside of our cooler. And it looks cluttered, but guys, this is like as good as it's gonna get. We have all the wet stuff on the other side of that barrier, so in case there's a leak, it's not gonna mess with the electronics. So that includes the perfusate container, the heated water container, and the pancreas itself, which in this picture we have a block which we used as one of those model pancreases to model the internal resistance. And then we have the pumps in the middle, as well as an oxygenator. And these are also separated from batteries on the left, so we don't get water on them. And these batteries have BMSs, so we don't have the same issue that the boat team had. And because we have an oxygen tank in ours, and it's a tight container, it's a lot more of a fire hazard if that goes off. And so once we close the lid, we need a way to monitor the data that's coming from our system, and that includes the oxygen, temperature, and the pressure. And so that's where our website comes into play.
So the transplant technician is always wondering what's happening in the box during the transportation. They don't want to arrive at the hospital having the pancreas already rotten. So we designed a local website that can display all the data our system gathered from the pancreas, including pressure, filter pressure, pump RPM, temperature, and oxygen level of the pancreas. But it might be a very difficult thing to stare at 5 different data at the same time because we only got 2 eyes. So we take out the most important data, which is the pressure versus time of the pancreas, and we set an upper limit and a lower limit at the in the website, and we measure the real-time pressure reading of the pancreas. Once it's too high or too low, our status will change from OK to 1, sending out a message to the transplant technician that they need to take care of the pancreas right now. And also, for the education purpose, we don't want somebody that's not familiar with our website to just directly go on the transplant mission. So we also embed a simulation program there. So it can mimic, and we embed a random function. So it can draw out all the graph like randomly, and so they will learn how to deal with all this like potential situation during their actual transplant mission.
So y'all are probably wondering, how do you even know that the organ is healthy, aka being viable? So we try to answer this question. We procured the pancreas, we try to prep it, closed up any leakage points, and connected it to our system. But unlike us in hospitals, you have actual surgeons who are able to actually correctly prep the pancreas. So we did have leakage occur, and with that being said, normally we had leakage occur, making it hard for us to get viability to the point we wanted to get to. But typically, you would first start with creating the perfusate. So perfusate has packed red blood cells, and this helps to transport nutrients and oxygen to the whole system once it's placed into the system circulation. And so after we've run the system, we're then able to collect samples to analyze. So analyzing them through pH, at-home pH, and lactate tests, which allows us to collect data on the metabolic metrics of the pancreas and compare it to a healthy pancreas to see whether it is viable or not.
Special thanks to our board of experts. These guys helped a lot in figuring out what we were doing. And we have a special thank you. He didn't know this was going to happen, but by popular demand, our main actor in our commercial, Cosmic Thunder, is making an appearance.
Alright, I know we're running a little bit behind. Everyone's going over like 1 minute, but we have one more team, so if you can hang out just a little bit longer than we had planned. Our final team is Deacon Dynamics. Woo!
Hello. Thank you all for coming today. My name is Parker. We have Tate, Angel, Alistair, and Caleb, and we are Team Deacon Dynamics. Today we'll be telling you about our continuously variable intake manifold Capstone project. So you may be sitting there wondering, what is an intake manifold? Well, I'm sure you've heard of an engine, or at least you know of one. Well, engines, they need air to come into the system. So what the intake manifold does is it sucks in the air and it distributes it evenly to each cylinder. And from there, the intake manifold balances the timing and the pressure of the air entering the combustion chamber. But there's a problem with modern intake manifolds. They're actually fixed in length, and that leaves potential performance gains on the table, as well as incomplete combustion, and it doesn't allow an optimal air-fuel ratio throughout a full RPM range.
Our vision with our project is to design this continuously variable intake manifold for internal combustion engines, looking at motorsports applications and other automotive manufacturers. And our three main goals are to create more complete combustion, eliminating some carbon monoxide emissions, and optimizing low RPM torque and high RPM horsepower. This all started with a partnership with our Wake Forest Formula SAE team, and through our design decisions throughout the year, we wanted to look at how can we move the runners efficiently, control this system, and then also looking at the material and the geometry of the runners, as well as the testing system that we can look at to validate our system. Further, our goal is to create a proof of concept that other Capstone years can build off of, and our foundation will be shown through this presentation.
Alright, so as Caleb said, our system has three main components that we're looking at. So first of all, with how to move the runners, we decided on actuation method of a pneumatic linear actuator. This allows us to use compressed air to move a actuator linearly. That'll allow us to change the length of our intake runners. And then for the intake runners themselves, we decided on Nylon X as a material. It's a carbon fiber reinforced 3D filament that allows rapid prototyping and is also able to handle the high temperatures of a running engine. And then for our testing system, we built our own mechanical brake dynamometer, which is a device that measures the horsepower and torque of an engine and will allow us to get testing data, comparing it to the baseline values for the stock. And as well as that, we also have carbon monoxide and carbon dioxide sensors to test our emissions coming from the engine.
So with these three main components, our next job was trying to integrate them into one design. So kind of the first step was trying to get this actuator actually on the engine that we have. And so we had specific mounts that we had to work with and design measurements. So with a lot of designing using a software called Lightburn, we actually went back to 111 and did cardboard prototypes to make sure that we were satisfied with the design and the measurements that we had. And then we laser cutted using metal, so we only had to do that once. For the intake runners, again here we did some testing on shorter intakes to make sure that we had the design correct, the measurements were right, especially the length of the connection as well as the diameter, so we didn't want any leaks on that back end of the intake. And then from there we printed 9 inches, so that intake will increase continuously 9 inches. As you see on the next photo, this is kind of what it looks like currently on the engine. So we have this actuator that sits on top of a metal plate with some supports here to help with those loads that we'll be feeling. And then right here is where the actuator moves, and so that will move out 9 inches, and then this connection is for that intake, so it will move 9 inches with the runner. Oh, and the engine, we needed to have some back calculations for this to make sure that it was safe when we ran it with the dynamometer. So we just made a simple L bracket for external support as well as cut a hole in the table for the exhaust manifold.
So now we had to make it move. It all starts with the air compressor, which shoots out air. Then it goes into a pressure regulator, which controls the pressure going into a system. Then after that, the air goes into a solenoid, which determines whether the actuator is contracting or expanding. And in addition to that, we use a DAC, an Arduino, the brain behind the system, and a string potentiometer, which is used as a feedback system. So it essentially determines that the actuator moved to its correct position.
One of the biggest challenges of our project in our testing system was coming up with a design that stayed within our budget. And so one of the coolest parts of our project was designing the testing system and figuring out how are we going to calculate and find the torque and horsepower coming off of the Suzuki engine that we got from Formula SAE. And so in going to a local junkyard, we were able to pick up a brake rotor and a brake caliper from a Chevy truck, actually. And so applying a load to the engine and the rotational force that's applied to the brake caliper The load cell will actually be able to calculate a torque value, and from that, we'll be able to find the horsepower of the engine.
Alright, so this is a video of our system functioning. It's our current prototype stage. On top you can see the linear actuator, and on the bottom you can see the runners. Essentially what's happening behind the camera is Tate is inputting a frequency which corresponds to an engine RPM into the system, and it's adjusting itself to the ideal position for that system for proper air delivery. This allows us to basically simulate air delivery and engine load conditions that would happen under normal circumstances, normal driving circumstances, and it's how we got our test data. So this is just a quick graph that shows basically our experimental distance versus our theoretical distance. The theoretical distance in orange is the ideal calculated length for a certain engine speed, on the bottom represented by frequency, and then the experimental distance is essentially just our accuracy within every single speed that we're looking at. And we've gotten it to under 5% error for pretty much the entire broadband range. So that's within our system requirements, and we're happy with that.
And with these results and the idea that this was to be a proof of concept capstone, and this is the first year that we are running this, we are kind of already thinking future steps if this was picked up next year by future seniors. One, we would love them for design them around the real engine mounting, so what would it look like if we actually place this engine back onto the motorcycle with the airbox and everything connected to it. Two, system operations using existing vehicle resources, so instead of a pneumatic actuator, maybe an electrical or a hydraulic using the oil pressure on the bike. And then three, optimizing intake runner design with CFD modeling, which is just computerized simulations to show the airflow throughout the manifold. And with that, we want to say a huge shout out to everybody that has helped us. Our panels have been amazing, and we really appreciate your help this year. And with that, thank you so much for listening.
Well, the class is over, but y'all technically stayed. So we do have time for one question, I think, for this team. I want to acknowledge that you guys are a minute under. So maybe take one question for this team, and then we'll wrap up. This is a tough project, so but anyone with no questions. Okay, I'm just going to wrap up really, really quick. Ben, I know we're over. Thank you all. Thank you all so much for being here. So on Wednesday, so if you want more time to talk to the teams and actually see what they did, we have another event. So Wednesday next week is going to be our design showcase. These are pictures from last year. If the weather is nice, then we'll be in the lower courtyard. If not, it'll probably be up on this floor. But if you did not get an invite to that and want an invite, let me know. I'm happy to coordinate with you. And again, just want to highlight all the people, all the faculty, staff, external technical mentors that have been involved with these students. I know I don't have time to read off all their names, but it makes it such a great experience for the students to have so many different people that they can consult with and get advice from. So thank you all so much. And that's it. Thank you all.